So good afternoon, everyone. Welcome back to Math 122. So I was just speaking with the class, if you're listening to the recording, that we're going to change the homework structure a little bit. Previously, I've been making the homework assignments due on Mondays, but I'm going to extend it from here on until Tuesdays, so that you have enough time to potentially come to my office hours and get last-minute help on the homework assignment before it's due. So today we're going to talk about, well, we're going to finish Chapter 4, and we're going to start Chapter 5. So the new notes for Chapter 5 are posted onto the Blackboard. We're going back to the pre-made notes. So I just don't like the pre-made notes for Chapter 4. They're no good. So, but we are going to go back for Chapter 5. So regarding your homework, you're going to have a homework assignment, which is going to be on 4.3 and maybe 4.4, which will be due not on Monday, but rather on Tuesday of next week. So that will be posted soon. For office hours this week, nothing changed, okay? But I do just want to reiterate that office hours are probably the number one way to get help for this class. I have a lot of students who come. You can come collaborate with your fellow students. You can hang out with me. We can do every single one of your homework problems if you want. Okay, but you have to show up. So if you have a hard time making yourself study, then do the easy thing and just put yourself in a room with me or with someone else in the MTC, and it takes a lot of the willpower requirement out of off of your shoulders. Okay, so make sure that you're using SI, MTC, and office hours to their fullest extent. Next quiz will be this Thursday, and it might even be the last quiz. I'm not sure. I think it might be the last quiz this Thursday. So that'll be on sections 4.1 and 4.2. Any administrative questions or comments or concerns before we start in on content? Yeah.
After this quiz, are you gonna do the drop, or is that at the end of the semester?
So I think on Blackboard there's already a drop category. I think maybe the drops are already incorporated. So if it's dropped the two lowest, I think right now, since you've only done only 6 quizzes are in the grade book, so it's six. It's your grade should be the best 4 quizzes or something like that. Does that make sense? So, yeah. Any other questions? Yeah.
Did you grade quiz 7?
I haven't graded it completely yet. I'm most of the way through, but I had a bit of a busy weekend, so I wasn't able to finish them up. But I'll have them back on Thursday. Any other questions? All right, then if not, let's review what we talked about last time. So, well, I guess really in all of Chapter 4, we've been talking about this theory of critical points, okay? And finding maxima and minima. So that's the plural of maximum and minimum is maxima and minima. And we're looking for basically the peaks and valleys, okay? So one of the things we noticed was that at the peaks and valleys, the derivative is always 0. So we found all the places where the derivative is 0, and we called those critical points, and then we had to decide whether each critical point is a local min, a local max, or neither of those two things, right? So this is what we've been up to so far, and the tools that we have for doing that are the first derivative test, which is just a question of whether the first derivative changes sign. So before and after this critical point, did our derivative change sign? And then we had the second derivative test, which said you can also check, well, are we concave up at the critical point, or are we concave down at the critical point? So both tests tell you the same information. The only tricky part is that sometimes the second derivative test will not work. Okay, sometimes the second derivative test will not work. And I'll show you an example of that maybe in a second. So far we've just been working on this find and classify, find and classify, find and classify, So you have to remember your factoring and all of that stuff. And then we talked about inflection points. So when do we have an inflection point? It's when the concavity changes, okay? So we use something which looks like this first derivative test, but is actually, we're checking the sign of the second derivative to the left of a potential candidate inflection point and to the right of a potential candidate inflection point, and checking, does the second derivative change sign? Because if the second derivative changes sign, we know that we went from concave down to concave up, or concave up to concave down, and we're going to have an inflection point when that happens. So that's what we talked about most recently. Are there any questions on any of that critical point, maxima, minima, inflection point stuff? Yes, Alex.
There were some questions on my homework. I just don't know if you got to this yet or if I missed it, but it was like, it gave us like a graph that was like the second derivative, and then it would be like, I think that's for like the critical points or something.
Okay, well, yeah, so there's a connection between, of course, the graph of the derivative and the critical points of the function, which goes like this. So say you have a function, right, which looks like this, okay? Looks like this, right? This is your function. Then there's an associated graph of the function's derivative, f prime, right? So this is the function's graph, or the derivative graph. So what we do is we take the slope at various points, right? And we ask ourselves, like, what is that slope and what's happening from left to right? And we're going to say, well, the slope for a given x value, I'm going to make the height of the function on the bottom whatever is the slope of the associated tangent line from the previous graph. So this tangent line has a positive slope. This one has a positive slope, but less positive. This one has a zero slope, and this one has a negative slope, and then the slope's getting more and more negative, right? So if I were to draw that as a graph where I make the height whatever was the slope of the previous graph, then I get a picture which looks like this, because this slope is positive, so this height is positive. This slope is positive but less positive, so this height is positive but less positive. This slope is 0, which is why the function goes through the x-axis here. And this slope is negative, which is why we have a negative height here, okay? So that's the graph of the derivative, right? So if you ask a question, you could say the following. You could say, I'm not going to give you this graph. You could say, I'm going to give you this graph and ask you, where does this one have a local max? Well, you have a local max in the parent function when you see the first derivative goes from being positive to being negative. That means that my function went from going up to going down, right? So when we see the first derivative passing through the x-axis, that's when we're going to have a max in our actual picture, right? But we may not actually have access to that graph for the purposes of identifying local mins and maxes, but we can still say that the graph of f has a local max when we hit this x value, because we know what's going on from left and right via the first derivative.
I think it gives the second derivative though, so how would you graph the second derivative? Like, how would you go from the second derivative to the just f?
So the second derivative could be used only to find where there could be an inflection point of the function f. So let me show you what I mean. And this is going to get really wonky here now. But let's say that our function f looks like... Okay, probably the easiest one to do would be something like x cubed, okay? So x cubed has an inflection point at 0. Agree? So how would you tell from the graph of the derivative of x cubed? Well, what would be the derivative of x cubed? The derivative would be 3x squared, and the second derivative would be 6x, right? So let me draw a graph of 6x. It's a line with slope 6, so it's pretty steep, but it goes through the origin. So this is the second derivative. So if they gave you the second derivative, you could infer, based on the fact that the second derivative went from being negative to being positive, that the associated components of the parent function went from being concave down to being concave up. So you could say, based on the fact that the second derivative passes through the x-axis on this graph, you could say that the parent function has an inflection point at x equals 0 based on that. Does that answer your question?
Yes, thank you.
All right. Any other questions before we move on to something new? All right, so we're going to do a little bit of group work today, but before we do that, let me explain a very simple concept, which is global min and max. Okay, so we've talked about local min and max so far, right? You can have multiple local mins, multiple local maxes, corresponding to the various peaks and valleys of your function, right? But what we mean when we say global max and global min, okay, is we want to take all of the local maxes and find which one is the tallest. Okay, that's the global max. Okay, it's like being world champion versus local champion, right? If you're like a local sports champ, okay, you win the state or whatever, then you're the best in the state, but you may not be the best in the nation or the world, right? So global, we're looking for the very, very tallest local max and the very, very lowest local min. Okay? Now there's two other things that we need to consider, which is that we always look for a global max or a global min on an interval, okay? And it's possible that a global max and min can occur at any of the critical points in this region, or it could occur at one of the boundaries. So let me show you what I mean. Let's do f of x equals x squared on the interval from -1 to 3. So what would that look like? It would look like, so here's -1. And this would be the point -1, comma 1, right? Then it comes down, and then we go all the way over to 3, and then we would have the point like 3 comma 9, right? 3 comma 9. So when we say global min and max on an interval, the interval is going to describe, like, I'm going to cut this graph off on the right and on the left, and I'm going to look for the tallest point in between these two goalposts, okay? The tallest point in between these two goalposts will be my global maximum. So there's two different places I need to check. I need to check all of the critical points where there could be like a peak or a valley, and I also need to check the boundary points. That is another place where I could encounter a global maximum, okay? So what we're going to do is we're going to list the critical points and the boundary points on a table, and we're going to check which one is the highest manually. So the critical points, well, I just take f prime is 2x, set it equal to 0. That tells me that x is 0 is a critical point. And then my boundary points will just be whatever are these two numbers, which in this case are -1 and 3. So I also put on -1 and I put on 3 here, and then I'm going to check what is the height of the function at each of these numbers. So for 0, I'm going to check, well, f of 0 is 0, and f of -1 is 1, and f of 3 is 9. So to find the global max, I just check for the tallest point. This is the global max. And for the global min, I just look for whichever point is the lowest. Okay, so even if you didn't have this picture, you can still say, well, I'm going to find the critical points, and I'll make a table, and the x values, which I'll put in the table, will be all of my critical points plus my boundary points. And then I'm just going to check well, what is the value of the function at each of those x values, and pick the highest one. That will tell us where is the tallest point in between these two goalposts. In this case, it happens to occur at 3, 9. And then for the global min, what am I going to do? Why did I circle that? I should have circled this. And then for the global min, it's going to occur at 0, 0, right? That's the lowest point. Okay, so I look in between these two goalposts for the tallest point and for the lowest point. I have to check the critical points and the boundary points. That's basically what I need to check. Okay, does this theory sort of make sense? Yeah, Braden?
For that, there wouldn't be a local max, right?
Yeah, so this function has...
The boundary points?
Are you asking if the boundary point constitutes a local maximum?
Yeah, you can.
It's complicated. Okay, so when we defined local maximum, what we said is that there's some small interval surrounding that point for which the function's highest value occurs at that point, which is not strictly speaking true if your function is defined on a larger domain. But, and this is getting incredibly semantic, if you consider the domain of the function to only be between these two values, then what you can say is like an open neighborhood of this point really just constitutes something which looks like the following, okay? Something which looks like this, in which case it is sort of the largest on that open neighborhood, but if you want to learn more about that, take a class on real analysis, and they'll tell you about a concept called relatively open or relatively closed sets. So the point is, we check all of the standard critical points, and we check the boundary points, and don't worry about calling this a local max or a local min. Just ask yourself, is it a global max or a global min, which is defined to be the largest possible value or the smallest possible value on this neighborhood. Okay? Does that make sense?
Yeah.
Yeah, I was just talking with someone earlier today at the Math Tutoring Center about that, and yeah, it's complicated. But thankfully, you don't need to worry about that. You just need to make the table, and you need to know you need to check the critical points, and you need to check the boundary points, and then from there, it's just pick the biggest number and pick the smallest number. Okay, any other questions on this stuff before we do some group work?
Can you scroll down to
Yeah. So what's written here is really just, look, where is the global max and min going to occur? Well, you just have to check what is the height at each critical point. Okay, what is the height at each critical point? What is the height at the left boundary point? And what is the height at the right boundary point? And then you just compare which one is tallest and which one is lowest. Okay? That's all that there is to global min and max. All right, so let's work on this group exercise, okay? So I'm going to set you all free to try to find the global max of this function between -5 and 14, and Jacob and I will walk around to help as needed. So, just to recall, find the critical points, CBs, make a table, on one side of the table, we're going to put the critical points and the boundary points, and on the other side of the table, we're going to ask ourselves, what is the value of the function? And then we're going to look for the tallest, find largest, and smallest. Okay, so get cracking with your friends, and I'll be walking around to help.
Okay, 6 and 16. Well, and 0.
No.
Right? What the fuck is a 3 to like? You took a 3 out.
Yeah.
Yeah, you do see after 3 out front.
Yeah.
Yeah, but you said that equal to 3 or 0 because it's a second term, right?
No.
Alright, I'll take your word for it. Because I'm not the challenge to do
Yeah, so we're trying to find the global maximum, which
I
is
really
really
don't.
the
Well,
statement
first we need to
about
find the
height of the function itself.
Yeah,
or make sure that they are. Oh no, wait, no, that's it. Well, yeah, that's when you find out what the fuck they're doing. I'm thinking of like this thing right here.
Because, I mean, you're right, we're not really gonna classify whether it's a critical point corresponds to the max or min. We're just gonna say, look, forget about whether it's max or min, whichever one of the critical points is the tallest, guaranteed to be the global max. See what I mean? So, yeah. We're not getting the critical points.
Yeah, I don't know, we kind of just like this time we actually had an equation to find it. Last time we just kind of like put a fucking graph on the screen. Right. Right. I don't actually understand what's.
There's just no way that's right.
Well, we're gonna
What?
Do you remember the graph was of the derivative?
Yeah, it should be.
So,
Yeah, but that doesn't make sense. No, the graph is of the vector function. I don't understand what's going on.
Found whichever is the highest y value. Make a table. We want to compare. We know that the max could occur at one of these. The other two places where it could occur could be -5. Just looking at the track, we're going to take all those and our original equation.
It's just like, don't understand, you get the correct equation, we're just gonna
then it still should be 0, right? Like in that situation.
So, I mean, you can do it in or you can do quadratic formula, or you can try to figure out what two numbers you multiply together to get 16, and add together to get 6. So, what two numbers can I multiply together and get statistically? It might be helpful to make a bit of a list, right? So 16 can be given by multiplying 4 times 4. Or it could be got by doing 2 times 8, or it could be got
we
by
can start listing these out.
So if we have these factors of 16, we want to find the two numbers or two factors such that if I can add or subtract them from one another, I could somehow get a negative sign each of those if I can do it. Yeah, whichever highest y value here is global max, and whichever lowest, right? What about the 3? Well, what's that? You have 3 times something
Regular equation, yeah.
is equal to 0. then whatever makes this
Okay.
zero,
It's actually not bad.
What types of numbers are there here?
Like -2,
So
you
we
get
find the numbers
little
which cause x squared minus 6 minus 16
8,
to be 0.
you get -3 minus 6.
Or another way of thinking about it is you can take this equation and divide both sides by 3.
-5.
Zero.
No, I did it better. I had -8 and 2.
Wait, no, are you right?
I think I did.
Wait, no, we've had this up.
Yeah, correct.
No, wait, it's -6.
Yeah, no, I'm right.
I'm stupid. So it is negative.
Oh, okay, so yeah, those are the boundary points.
-2 and 8.
What else do we have to do? We still have to check the critical points, right? So we got the derivative. Let's figure out the critical
No.
points. But we
I
got
just
we
wanted
gotta
to
take some
add
critical
one.
points.
No.
Yes.
And set these to
Negative.
0.
It needs
So
to
for
be
here,
-8
we gotta
in
factor
order to get the 6.
No, it doesn't.
'Cause the
It's
6 is
-6.
negative.
No, but if you do this, you still get that. Look.
She just figured it out.
X squared plus 2x
It's a factor.
minus
Can you
8x
help me out with that?
minus 16. 2 minus 8, -6.
Whatever. Okay, it's 8 and 2. 8 and negative 2.
8 and -2. It's because this is like, it's x minus 8, x plus 2. You know what I mean?
What? I'll write down your silly little numbers first.
I'm right.
I'll write down your silly little
It's
numbers,
just this.
and then I'll be the judge of what's happening.
I'm right.
Yeah, what am I gonna do?
Don't cry.
I cry a lot.
Ask for help.
I'm gonna ask you for help.
Like, that makes sense, right? Because you're like,
What doesn't make fucking sense to me is that we have a -6. And if you
no,
take
no,
I'll have
no.
to solve it
You're
first
just
to figure out.
confusing yourself because it's like, this is the -8 in the equation. That's how you know.
No, I know, but what I'm saying is that
That one might be negative.
yeah, no, this is this.
Alright.
Wait, is this what you had in the belligerently stood?
Yeah.
We've been arguing.
Yeah, that is what I had.
Oh, okay. I've been arguing
About the factory?
No, I've been arguing with a brick wall. Don't worry about it. That was me just reading everything. It's because this wasn't changed by having these, so I was looking at these. And
Yeah.
But in reality, it was me.
I hope these numbers are right. I typed
Okay, does anyone want a little bit more time to work? Okay, take about another minute or so, okay?
Yeah, so. What multiplies to get -16 and adds to get -6. Is that a part of your like equations
What happens if you plug in 0? You get a 3 times -8.
Maybe it is possible.
It would be a 0 if you had an x right there. See what I mean?
I thought.
Well, if you had an x right there, then you'd have 3x times x. So what happens if you plug in 0 into this? We're trying to find critical. 0 is the critical point. 0 is the other equation. It's usually kind of -8 minus 2, so that's not good. That's right. Yeah, sure. All right, let's talk about it as a group. So what do I need to do first? Someone help me. I'm lost. Sorry? Yeah, derivative. First thing to do is find the derivative. And why do I want to do that? Well, that's going to help me do step 1. Find critical points. What is a critical point? Can someone explain it to me? Because I forgot.
Where the first derivative is 0.
Exactly. A critical point is any x value where the derivative is equal to 0. Now I remember. Okay, so let's do the derivative. We get 3x squared minus 18x minus 48. And we set that equal to 0. And then I can divide both sides of this equation by 3 and cause no harm. Oops, not 18, but 6. And then I can solve this quadratic equation in any number of ways. I could use grouping, I can use regular factoring, or I could use the quadratic formula, okay? But this class isn't about those skills, so if you need help with that, please come see me in office hours. So what we can do here is, I think x minus 8, we want to find two numbers that add together to get negative 6 and multiply together to get negative 16. Those two numbers are negative 8 and positive 2. So x is going to be equal to either 8 or x is going to be equal to minus 2. So those are our critical points, and now we need to make a table. So I have the table written here, and I need to do first the critical points and the boundary points. So the x values are going to be, well, if you put them in order, negative 5 is the left boundary point, and then I have negative 2, and then I have 8, and then I have 14. And what should I do with these numbers? Yeah, we're going to plug them into the original function. So some students had a question which was, well, should I be plugging it into the original function or should I plug it into the derivative? Right, well remember, we're looking for the global max. This is a question about which point is tallest, which point is shortest. That's a question about the height of the function, so I should be plugging into the function itself, okay? So I plug into the function itself and, okay, what do I get? I think it's negative 58, 104, is that right?
Yeah.
And then negative 396, and then 360?
Yeah.
Okay, so those are the values that you can get. I'm glad I wrote them out in advance. So which one is the global max? Yeah, it occurs at x equals 14. This is our global max. And our global min is at 8. So that's it. So, again, it's find the critical points, put them in a table with all the boundary points, plug all those things into the function and look for the tallest one or the shortest one. Okay? Any questions on that whole process? How do we feel about it? Thumbs up if we had a quiz on this on Thursday, would you get an A or an F? Real high for me, please. Thank you. Excellent. All right, it looks like people are happy with this, so we're going to move on. So I'm going to skip section 4.4. It's just applying this min-max theory to profit, revenue, and cost functions, okay? So if you know how to find the critical points of a function, well, if that function happens to describe profit or cost or revenue, you can find the critical points of a cost, revenue, or profit function, all right? So same exact thing. I'm still going to probably assign some problems from section 4.4, but nothing that you wouldn't be able to do with what you've already learned in 4.1 through 4.3. Okay? So final questions, comments, or concerns on chapter 4 before we go to chapter 5? All right, so can someone give me like a 1 or 2 sentence summary of what we learned in chapter 4? What was chapter 4 all about? know, it's a challenging question, but give it a shot. You can talk with a partner if you want to come up with a summary on your own. Take 2 minutes, talk with a partner, and try to come up with a summary of what we learned in chapter 4.
You can use the first and second derivatives to calculate points on the function's graph.
That's facts.
I feel like that sums it up.
I would say so.
Is it hot in here?
Yeah, it's always hot in here.
I was a little sweaty when I came in.
From East Squad to here.
Ooh,
Sun's beaming.
that's hot.
Well, sun's beaming on me, and I walk in here and I'm not sweating. I'm like, I get in here and it's like just warm enough where I continue to be the same heat I was outside. And I'm like, dude, I'm out of the sun. Like, give me a break. It's
What
okay.
is it really?
Same.
It is.
I've lived here my whole life. I hate it.
Where are you gonna move after?
Anywhere but here.
Anywhere but here?
Or Florida.
That's how I used to feel about Indiana, and then I came
I
here.
said or Florida. I don't want to
That's
live
what
in
I'm
Florida.
saying, though, is that for
Disgusting.
Florida.
I love being warm. I would take this over.
Well, yeah, back home, yeah, like literally, there's like my grandpa sent me pictures of it.
Do y'all
like, at
live
my
here?
house yesterday.
It
No,
gets
I'm from
worse.
New York.
Yeah.
July.
Oh, God.
This is what it looks like at my house.
What messes me up is the fact that the summer lasts for like 6 months.
Yeah.
It goes from like May until October.
Like
I'm sweating about that.
that was
I love that
yesterday.
you have a high-five.
All right, have we got a good summary? Does anyone want to share their summary from their group?
Back home. It's
Pretty
more
please.
Yeah, I don't even want to look at this.
You could do it for me. It would really warm my heart. Please.
Using derivatives to find like critical points.
Okay, using derivatives to find critical points. To what end? Can someone answer that? To what end? Why do we care about that? Yeah.
Finding information that may be important on graphs.
Finding information that might be important on graphs, like what? Sorry? Yeah, like where are the maximums and minimums, right?
With all that.
I, as a business person, might want to maximize my profit. Or I might want to maximize how far my car can go on a single tank of gas, right? Or I might want to maximize, think of anything that you want more of, or anything that you might want less of, yeah.
So I could use this graph to find out how much gas I need to get somewhere.
Well, sure, or you could say, like, what's the optimal speed to drive in order to maximize your miles per gallon, right? How many miles per gallon you get depends on how fast you drive your car, right? You hear about people who are like, for the car commercials, they say, oh, you get this much mileage in the city and this much mileage on the highway, right? There's an ideal speed to drive your car to maximize miles per gallon, right? And if you drive like 100 miles an hour, okay, you're going to be revving the engine so much that you're going to use much more gas. Even though you're going faster, your mileage will be worse, right?
How did you use these equations to show us how to do it?
Can I use these equations to show you how to do it? Well, look, the point is not necessarily...
You're making the engine harder. Of course it's going to use more gas.
Okay.
I don't think
This is sort of neither here nor there. Maybe I'll come up with an example. I'll come up with an example function for you which describes how this works, okay? And I'll show you how you can come up with an equation and how you can find its maximum in order to find the ideal speed to drive in order to maximize your mileage. Deal? Okay, great. Well, maybe we'll do that on Thursday. Okay. Well, let's move on to chapter 5.
Yeah, if you like let off the pedal and let yourself coast.
3-second trip.
But the entire time you're doing it, you're pushing on the
Yeah, 3-second trip. Yeah. Okay, so what are we doing? Well, chapter 5 is about something completely different. So far, what we have been talking about is if I have a function which describes a quantity, I ask myself, how does this quantity change in time? Now what we're going to be interested in is, if I know how a quantity changes in time, what can I say about the quantity itself? Okay, so one thing is, I know the quantity, say something about the rate of change. Now we say, we know something about the rate of change, say something about the quantity. Okay, so an example would be, if you know, like, for example, how far away you are from home after t hours, you could surmise how fast you were driving at time t. Yes, that's derivative. That's what we've been doing so far. But now we're going to ask the reverse question. We're going to say, if you know how fast you were driving at time t for every time between now and 1 hour from now, how far away was I at the end? Okay? So this is a question about, we're switching our frame of reference from rates of change to a concept which we call accumulated change, right? Like, for example, if you could say, I earn money at a certain rate. I'm earning $20 per day. How much do I have after a week? Right? These sorts of things are to say, I know I have a rate at which something is changing. How does this rate of change accumulate over time to produce like a net effect? That's basically where we're going with chapter 5. Okay, and it is in some sense a reversal of the question, and it is also sort of a reversal of the process. So we're going to learn through chapter 5 and 6 about the concept of integration, which is can be thought of as a reversal of the process of differentiation. So far we've been taking the derivative of functions. What we're going to learn in chapter 6 eventually is how to do an antiderivative. How to go up the ladder instead of down the ladder, okay? That's basically what where we're going. So we'll start very simple, right? We'll start very simple with you've probably seen that video, which I love, of the person who's like asking their friend, they're driving in a car, and they ask their friend, like, if I drive 80 miles an hour, how far do I go in 1 hour? And the person's trying to do like this mental calculus of like, what's the diameter of the wheels on my car or whatever. It's like, no. You just take 80 miles an hour times 1 hour, that's 80 miles, right? So that's the idea that we're going to do here. So what is going on with that question? Well, we say we have a cyclist traveling at a constant velocity of 15 feet per second for 3 seconds. How do we get the total distance? Well, we use the equation that the velocity is the distance divided by the time, yeah? And we could say, well, therefore, the distance is given by the velocity times the time. So how fast was I going times how long did I go? That gives me 15 feet per second times 1 second. The units of seconds cancel, and we get, not 1 second, 3 seconds. And we get 45 feet. 45 feet. Okay, so starting off super simple, but it's going to get more complicated than that. Okay, so first of all, let's try to sketch a graph. Okay, let's try to sketch a graph. So I'm supposed to do the graph of the velocity. So the velocity is given by 15 feet per second, and it's 15 feet per second for the whole time. It's a constant velocity, meaning that the velocity is a constant function, okay? So a constant function looks like this, and it's a 3-second trip, and this height here is 15. Yes? 15. So now let's ask a question. This number 45, what does the number 45 have to do with this picture? How does the number 45 appear in that graph? Yeah, Aiden?
Is it the area?
Yeah, it's the area. If I were to close this box, the area of that box is given by the width times the height. Height. The width times the height. Yeah, so if you drop a box, 45 represents the area of the box, yeah? Oh no. Well, okay. I guess we want to just do this. So, this is 45 units squared, right? 45 units squared. So we find out that the velocity, okay, the area under the velocity curve tells me what is the distance traveled, okay, the area. All right, let's do another one. This one's going to be more complicated. Now the bicyclist is going to travel at a constant velocity of 5 feet per second for 2 seconds, and then at 15 feet per second for 1 second. So what does that look like? Well, the distance traveled, okay, can just be the distance traveled in the first 2 seconds plus the distance traveled in the last second, right? So that could be distance will be 5 feet per second times 2. So why don't I do feet per second times 2 seconds. That's the distance traveled in the first 2 seconds, and we add that to the distance traveled in the last second, which was 15 feet per second times 1 second. So cancel, 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 cancel. We get 10 feet plus 15 feet equals 25 feet. Okay? And let's do the graph. So this time the graph looks like this. It's 5. And then it's 15. Yeah? So this is what the graph looks like. And, well, again, the distance that we found in part A appears in this picture in the following way. The 10 feet, that's the area under this part of the graph. And the 15 feet is the area under this part of the graph. Which, of course, if you sum the area of 2 rectangles, then you can get the area of this kind of L-shaped block, right? You get the area of the L-shaped block by adding the areas in pink and blue, right? So together, 10 and 15 make 25, which tells us the area of this entire L-shaped block here, right? So distance traveled is basically accumulated velocity, okay? We travel at a certain velocity for a certain amount of time. We accumulate velocity as distance. Questions so far? Does this feel pretty intuitive? Okay, I think the pictures should hopefully help. All right, let's see something harder. Aha. Now what do they tell us? Now they tell us that the cyclist is cycling their little heart out in such a way as to have a velocity which is proportional to the time, meaning that the longer I go, the faster I ride my bike, right? So what does this function look like if I were to draw its graph? V of t equals 5t, that is a linear function with slope 5. And the story that this picture tells, is that, look, I started off cycling I was stationary initially. And then I started going faster and faster and faster and faster and faster, because remember, the height of this function tells me how fast I'm going, and the height is increasing. So the velocity is getting larger and larger and larger and larger, which means I am going faster and faster and faster. I'm accelerating, in other words, right? Okay, so, and we do this for how long? 3 seconds. So, 1, 2, 3 seconds. How can I figure out how far I went? Because I can't just say, well, I was going this many feet per second for this long, because my velocity is changing all the way throughout this thing. So what can I do? What can I do? If I'm speeding up and speeding up the whole time, how can I figure out how far I went? Well, I can't just multiply my velocity times the time. Yeah, what can I do?
Division you gotta do?
Some kind of division? No, no division. But let's take a look back at these ones. How did this distance manifest in the graph? The distance manifests as area under the curve, right? What would that look like for this picture?
Times 1 plus 5 times 2 plus 5 times 3.
Not quite. What I am looking for here is, what is the area under this curve, which happens to be a triangle, right? Okay, I can't draw it that well. We're looking for this area here, shaded in blue, right? Is there a way I can figure that out? What kind of shape is that? It's a triangle, right? What's the area of a triangle?
1/2 base times height.
Yeah, area is 1/2 times base times height, which in this case is 1/2. The base is 3. What's the height? Is it 5? 25.
Or 15.
15. It's 15 because this is 5t and t goes up to 3. So the height here will be what you get when you plug in 3 into the function 5t, which is 5 times 3, which is 15. So we get 45 over 2, or 22 and a half. Okay, so now we're getting somewhere. Yeah, Alex.
Could be wrong, but is it multiplying by 1/2 the same as divided by 2?
No, you're right.
There you go.
You're. Oh, you're saying, am I gonna have to divide something? I see.
Yeah.
So you're saying you're.
It's like half of the square, so you have to divide by 2.
I see what you mean. Yeah. I mean, that is where the area of a triangle comes from. Is because the area of a triangle is just half of the area of a rectangle, right? So yes, you're correct. Division is involved. All right. It's about being technically correct, the most important kind of correct. All right. So any questions on this? So what? Now we've done something interesting here, right? You knew already how to figure out how far you went if you're traveling at a constant velocity for a certain amount of time. But now our velocity is doing all sorts of crazy things. You can't even say, like, I was driving or riding my bike at 5 meters per second. You were only doing that for like a fraction of a millisecond, right? You were only riding your bike at a certain speed very momentarily because you're accelerating throughout this time period, right? But we can still figure out how much distance was covered by recognizing that the concept here is to find the area underneath this function. So whatever kind of function we have, maybe we can't easily figure out what is the accumulated change, but we can find this area. Well, the area is the accumulated change. So as long as we can find the area under the curve, we can understand how much distance was traveled, right? Or how much change was accumulated. So that's the entirety of this, of the rest of this class is going to be dedicated to understanding how to do that. Which you say, well, isn't it easy? You just apply the formulas which tell you how to do area, and then you're done. Except, what if... Okay, so based on our... Write down a rule. So, look, area under curve. That's what it is. So where's the catch? Where's the catch? Well, the catch is, what if your velocity function looks like this? Then what am I going to do? Well, I will still want to know how far I rode my bike. So I know I need to find the area of this shape. But this shape is not a shape that I can easily find the area of, right? It's like all curvy and wonky. There's no formula for it, right? So that's going to be the subject of our study for the rest of this class, is trying to understand how do I figure out what that area is, and thus understand the accumulated change. So distance traveled, money made, units sold, whatever, right? I need to understand what is this area under this curve, and that's what we're going to study for the rest of this class, basically.
Like the year or the...
Like the year. Yeah. It gets complicated. Trust me. Okay. So, what are we going to do? So, let's talk about Riemann sums. So, Riemann sums apply the following logic. Extremely simple idea. Okay? The extremely simple idea is to say that, well, the area of this shape is not that different than the area of this shape. Okay? At least it's fairly close. Agree? Fairly close. And in fact, we could do even better than that. We could say that the area of this shape is even better approximated by the combined area of these two pink rectangles. Yes? And in fact, the more and more rectangles we use, the better and better our approximation gets. So let me show you what I mean. So I'm trying to find this area. Well, what if I were to do something extremely fine, like this? Right? You get the idea. Okay, ... The point is, if I use a lot of very, very thin rectangles, yes, then the combined area of these rectangles will be very, very close to the actual area that I'm interested in. Do you see that? The reason being that here's my error, okay? My error is basically just this bit that I got that I wasn't supposed to, and then I have this bit, which I didn't count, but I should have, And then I have this part, which I counted but I shouldn't have. And then I have this part, which I counted but I shouldn't have. And then I have this little part here, right? So you can see that the error, okay, of my approximation here is quite large, okay, because I'm missing large parts of the actual area, and I'm adding large parts that actually aren't there. But what does my error look like here? My error is just these little bits, right? Just these little bits. And you could see that if you were to add up all of the error in this one versus all of the error here, you're going to have a much smaller error, right? Basically, how many times can I say error in 1 minute? Probably a lot. All right, so is the idea clear? But like what we're going to do? Taking a bunch of tiny areas. You got it. Exactly. So we have to come up with a way of writing down a bunch of tiny areas, right? And the way we do it is by using summation notation. So let me maybe remind you what summation notation is. So we do one of these, a sigma. I'll make this one nice. After that, henceforth, they're going to look like this, probably. Oh my god, that's too many squiggles. That's how I'm going to draw them. They won't look perfect. But anyways, you get the point. So we do like I equals 1 to n, and then like n, okay? Let's do an example. What this means is, look, you're going to let I range from 1 to n. So you're going to let I take each integer value between I and n, and you're going to sum up like a function of I. A function of I. So what does this mean? Well, you let I take each integer value between I and n, plug in to f, and sum. Okay, so what would we get if we did the sum from I equals 1 to n of f of I? We're going to get f of 1. Sorry, not I and n, but 1 and n. Why don't I make it k and n? Okay, so I changed this. We're going I equals k to n, and we're going to do each integer between k and n. So we're going to get f of k plus, and then we're going to do the next integer, f of k plus 1, plus f of k plus 2, plus dot dot dot, f of n minus 1, plus f of n is the last one we'll do. Okay, so let's do an example. Let's do the sum from I equals 3 to 7 of I squared. Well, the first thing we do is we let I be 3. So we do 3 squared. And then we go up by 1. We let it be 4. So plus 4 squared, plus 5 squared, plus 6 squared. And I know when to stop because the stopping number is on top. We're going to go all the way up to 7 squared. Okay, so if you did this, you'd get 9 plus 16 plus 25 plus 36 plus 49. And whatever that number is the number which is represented by this notation. All right, do we have questions on that? So the sigma means we're doing a sum, S for sum. The bottom tells you where to start, and then you just go, you let I go up by 1, up by 1, up by 1, up by 1 until you hit this guy. And for each I, you're going to plug it into whatever is the function. Okay, plug it into whatever is the function. So in this case, it was I squared, so we did 3 squared, and then we go up by 1. Now we do 4 squared, and we go up by 1 again. 5 squared, 6 squared. And we stop at 7 squared because 7 is the largest number that we're supposed to do. Now, can you raise your hand if you've seen this notation before at some point? Okay. You'll probably seen this notation at some point. If not, this is how it works. Okay, so now we're going to get nasty. We're going to write down some Riemann sums, which tell you the area under the curve f of x from A to B using n rectangles. Using n rectangles. Okay, so let me just draw a picture of what we're doing to remind us. So here's A, here is B, and here is f of x, maybe, could look like that. I'm interested in approximating this area. Is approximated by well, okay. Let me rephrase. The area under f of x from A to B is approximated using n rectangles by the following expressions. So what do I mean by n rectangles? I mean, for example, if n was equal to 4, what would we do? We would divide this thing into 4 subregions, and I would make rectangles which look like the following. Here's my first rectangle, and my second rectangle could look like this maybe, and my third rectangle could look like this, and my fourth rectangle maybe could look like this. Okay? So that's the idea of what we're doing. So when I say area under f of x from A to B, I mean I'm going to start counting area once I hit x equals A, and I'm going to count up area, and I'm going to stop counting once I hit B. Okay, so that's what I mean when I say area from A to B. Okay? Are we okay with what we're trying to express? All right. Now comes the bad part. Using a left-hand sum, actually, before I even say that, let me say, first off, the width of every rectangle is, and we use this symbol here, delta x, to refer to the width of one rectangle. Well, it depends on how long is the interval and how many rectangles are you going to use. So the length of the interval is b minus a, and we just divide that evenly by the number of rectangles that we have. So b minus a over n. So in this case, you would do b minus a over 4. Okay? So that's the width of every rectangle. So, to do a left-hand sum, we're going to do the following. We're going to use the sum from I equals 1 to I equals 0 to n minus 1. I equals 0 to n minus 1 of delta x, that's the width of each rectangle. And then I need to choose, well, what is the height of each rectangle going to be? If I use a left-hand sum, I choose the height of the rectangle to be the height of the function on the left side of each subinterval. So that would look like the following. We'd use these heights here, okay, to make the height of my rectangle. So the height of my rectangle is going to be f of a plus I times delta x. Okay? F of a plus I times delta x. So what is that? That is the height. And this is the width of one rectangle. Okay, the height and the width. So I think the part that is probably going to be the most confusing to everyone is, what the hell is that? Well, what that is the following. Ask yourself what it will be when I is 0. When I is 0, this part goes away, meaning that the height of the first rectangle should be the height of the function at a. In other words, we use this rectangle. Then what happens when I is equal to 1? When I is equal to 1, we're going to take a and we're going to add 1 times delta x to it. Where does that put our x value? That takes our x value from a, we add delta x to it, that gets us to this point, which should be the height of this x value under the function should give us the height of the second rectangle. And then what happens? Then I will be 2, and we will do f of a plus the width of 2 rectangles. That will take me from a to here to here. And then what should the height of the third rectangle be? It should be the height of the function on the left side of that subinterval. Yes? Oh, I'm running out of time. Sheesh. So anyways, I just wanted to give you that time. Sorry, I almost went over. We'll talk about the rest of it next time. I just got so excited about Riemann sums.